A car on a highway. The speedometer reads 60 miles per hour. That's the rate of change of position right now, not the average speed over the trip, not the speed 5 minutes ago. Right now, in pharmacokinetics, the concentration time curve is the position. The derivative, dCdH, is the speedometer. How fast is the drug concentration changing at this exact moment? Calculus reads the speedometer. Draw a concentration time curve. Pick 2 points and connect them with a straight line. That's the average rate of change between those times. Now bring the 2 points closer together. The line tilts. Closer still. In the limit, as the gap shrinks to zero, the line becomes tangent to the curve. The slope of that tangent is the instantaneous rate of change. The derivative. This limiting process is the foundation of calculus, and it transforms a static curve into a dynamic story of how fast things are changing. A few rules cover most of biology. The power rule, the derivative of x to the n is n times x to the n minus 1. The exponential rule, the derivative of e to the x is e to the x. The exponential function is its own derivative. This is why first-order elimination produces exponential decay. It's the only function whose rate of change is proportional to itself. The constant multiple rule, the derivative of k times f is k times the derivative of f. The sum rule, the derivative of a sum is the sum of derivatives. With these 4 rules, you can differentiate almost any function in pharmacokinetics. The chain rule handles compositions. If effect depends on concentration and concentration depends on dose, then the derivative of effect with respect to dose equals the derivative of effect with respect to concentration times the derivative of concentration with respect to dose. E ratios. The first gear converts dose to concentration, the second gear converts concentration to effect. The overall ratio is the product. INTSB sensitivity analysis asks, how does changing parameter k affect the output? The chain rule propagates that perturbation through every equation in the system. The Michaelis-Menten equation V times S divided by Kim plus S requires the quotient rule to differentiate. The quotient rule, the derivative of f over g equals g times f prime minus f times g prime, divided by g squared. You need this to find the rate of change of enzyme velocity as substrate changes. The product rule, the derivative of f times g equals f times g prime plus f prime times g, appears whenever 2 quantities multiply, like volume times concentration. Most real functions depend on multiple variables. The concentration depends on clearance and volume and dose. Partial derivative holds everything constant except one variable and differentiates with respect to that one. The gradient vector collects all partial derivatives into an arrow pointing uphill. In gradient descent, the mountain biker rides opposite the gradient, downhill on the lost surface. In mol, the photographer computes partial derivatives of the log likelihood with respect to each parameter to find the peak. Partial derivatives are the multi-dimensional speedometer. Derivatives read the instantaneous rate. Basic rules handle powers, exponentials, products, quotients. The chain rule propagates through compositions, gear ratios for sensitivity analysis. Partial derivatives extend to multiple variables, the gradient for optimization. Next, putting it all back together.